Okay, on today's screencast, we'll learn about a way of displaying data in circadian biology in general, in biological rhythms in general, and it's a very graphic and easy way to display raw data that comes from biological rhythms. And we call this the actogram. The name comes from the fact that this form of these graphic displays were first used to display activity either of humans or animals, that you have some way of recording their activity, such as infrared interruptions or running wheels, or running wheel where the animal is running and you have some way of counting how many turns that animal makes. But in principle, you could use this type of display for any type of rhythmic data. For instance, the levels of a hormone that is released on a rhythmic fashion, or the amount of REM sleep, for instance, or any other type of biological variable that oscillates with a specific period. Um, so what um, we do here is essentially plot the data daily, but then in such a way that becomes very easily to detect whether that data is rhythmic or not. So let's start from a case in which we have, let's say, a mouse or a rat that has free access to a running wheel, and I tell you, the maximum that this animal can run in revolutions per minute, RPMs, is, let's say, something like 500. So the activity can go from 0 to 500. And I tell you that this animal is in an environment where the light dark cycle consists of this bar here. So dark will be represented by this dash area in the plot. Let's make this a little bit bigger on either side. And let's say that the animal is half of the time roughly in the dark and half of the time in the light. So we know, I tell you, that the lights go on at 8 a.m. and they go off at 2000 or 8 p.m. We'll always use military time in circadian biology because it's easier to quantify and refer to. So essentially, if you look at a typical mouse, rat, or hamster, which are nocturnal rodents, what you will see is that these animals are highly active when the night starts, and they are virtually only active during the night. So what you will see is that you may have some blips of activity here during the daytime, but then as soon as the lights go off, this animal will hop on the wheel and will increase its activity very much, and sometimes it will decrease towards the end of the night. That's typically what these rodents do. And then, when the day starts, they go back to very low levels of activity. Of course, I didn't tell you, but this is a 24-hour period. So we go, let's say, from noon here, 12 p.m., to 2400 or 0 of the next day, right? So you can see here that this animal ran particularly during the night, and I could ask you, well, is this a typical day, or how do you know that the animal is going to do the next day the same thing? So let's first color this in black, so then it's easier to visualize. You will see why. So we'll mark the bulk of the activity in black, okay? And then the next day I tell you, can you please check again what the activity of this animal was for day 2? under the very same conditions. So you just do the same plot, but I won't put the units to simplify, and essentially what you see is that on day 2 the animal did something slightly different, right? But essentially the activity also took place during the nighttime. Okay, so again we will color these to make it very prominent. So this is essentially all the bulk of the activity. And then, I'm insistent, I'm your advisor, and you need to do this. So you go and I tell you I want to see whether this is the case also for day 3. So you do exactly the same, and essentially the animal does something very similar, some slight differences. Of course, each day is going to be a different pattern, but the overall nocturnality will remain the same. In other words, the animal will still be active during the nighttime if it is a normal behaving mouse or rat. So I'm just blackening these. So again, we do this for each day. And then on day 4, you do exactly the same. And this is what it look like. And essentially, you can see that every successive day, when the night starts, this animal starts with an activity that is roughly 500 revolutions, and then it goes down on each successive day, as you can see here, on each successive hour. Same here, the animal is running, starts with very high levels and it goes down. Same on day 3 and same on day 4. So, but let's say that you really want to know whether this animal is rhythmic for a very long time. Let's say that we want to do an experiment that lasts something like a month. Well, you will tell me obviously, well, I need more space in this page because I won't be able to fit 30 days in this plot. So let's do something which is essentially what will lead to the so-called actogram, and this is to shrink this, okay, and then continue with our little plots, okay. Oops, sorry. So we'll continue with our little plots. So again, this is too thick. There you go. So this is going to be like this now every successive day. And then basically what you will see is that on each successive day you have something very similar to what you saw before. So let's do it now this way. And if we continue and continue, what you will see is that on every single night the animal was active during the night, and we could simplify this kind of plot by just drawing the activity bars, because we all know that on every day we're just plotting wheel running revolutions per minute, and essentially whenever you see black, that means that, as we see here, that means that the animal is highly active running on the wheel. So if we now erase this and let's see, and let's do just a single plot of what would be roughly a month of activity in this same animal, if you had the light-dark cycle here, as we had before, and this is a nocturnal animal, this will essentially look like this. On each successive day, you will see activity here, and activity here, so this way, an activity here, and essentially on each successive day what you will see is that the animal is active during the nighttime. And this is an actogram, so we usually have margins here, and this you know that goes from 0 to 24 hours, or from noon to noon, but if you just quantify it in hours, it's a 24-hour actogram. What you will see is that the animal on every single day, and this is typically what a mouse or a hamster will do, and I will show you later in class plots that are for real, that are generated by an animal running on a wheel. And you can keep this animal for 2 months if you want. You will see the same trace. So there's a few things that you can draw from this type of displays. The first thing that you can see that is very clear is that this animal is very rhythmic. In other words, an animal that has a broken circadian clock, that has no ability to time its behavior, it would not look like that. If this is night and day, it would be something like this. On day 1, the activity would be throughout the day. On day 2, at different times, but also throughout the day. On day 3, it would be like this, and so on. And essentially, this is what an arrhythmic animal would be, okay? However, if you look at a normal animal, and we will see later that animals in which you lesion some parts of the brain that render them arrhythmic, they will exactly look like this. However, in a normal animal, in a normal mouse or rat, you will see that the activity is displayed every single day at the same time. And how do you know that it's every single day at the same time? Well, you could say, well, let's look at when the animal starts running on the wheel, and we'll make a little dot here. Let's do it in red so it's clearer. So you can see that every single day the animal is getting to run on the wheel at, in this case, the time that we said was 2000, so 8 p.m. So not only this animal is rhythmic, but also you can tell me just by doing this little exercise of marking when the activity starts each day that the animal is very accurate, starting every single day at the very same time, and therefore not only this animal is rhythmic, but also the period of its rhythm is exactly 24 hours, right? Because if you count how much it took from the time it started running here, right, to the time that it started running the next day, that's going to be 24 hours exactly. And the same will be true for the next day, and so on. So in this case, you know that it's a 24-hour rhythm, because from day to day it takes exactly 24 hours for the animal to do the same, start running on the wheel. Or another way of putting this is that the line that these dots are describing is a perfect vertical line. In other words, it's perpendicular to the time axis, right? If that line was not exactly 24 hours, if that line was not exactly vertical, that means that the animal would have a period that is different from 24 hours. So let's look at that. So here, okay. So now let's plot an animal that has, let's say, this kind of activity. So again, this is an actogram now. We're looking at 24 hours. This would be hour 0, hour 24 for each successive days. And days are now, as you know, vertically stacked. So these are days. And this is day 1, day 2, day 3, day 4, day 5, 6, and so on. And let's say that this animal, instead of doing what we saw that the previous animal did, that was on successive days, and I'm just drawing lines now for activity to simplify the display of the actogram. Let's say that instead of doing this, which is to start exactly at the very same time on each successive day as the previous animal that I schematized did, this animal does this. I see that on day 1, the activity was here. On day 2, started a little bit later. On day 3, a little bit later, and so on. And then it will come off the plot, right? But if you imagine that this came off here, this time here represents the beginning of the next day, so it will appear here, right? And then if you imagine the second line being here, this will represent the next day here, and so on. So these bars will eventually reappear here, okay? So if I ask you now, how long is it taking for this animal to start running on the wheel again, and let's do the same exercise of labeling the red with red dots the onset of activity. Well, it's very clear that for these animals, it's taken it, in this case, remember, it took this animal exactly 24 hours to go from onset to onset. In this case, however, it is pretty clear that it's taking this animal a little bit more, right? So in other words, from onset of activity on day 1 to the onset of activity on day 2, the period was, instead of 24 hours, let's say 24.3 hours, okay? Which would be roughly 24 hours and 20 minutes. And then if you measure that on day 2 to day 3, you'd get very much the same value, and so on. So what that means is that if the line that merges all these dots that represent the onsets of activity does not represent a vertical or a perpendicular to the time axis, right, as this one did. If the line is drifting to the right, that means that the period is longer than 24 hours, right? Because on each day, the animal is getting onto that wheel to run a little bit later. However, you could imagine a scenario in which another animal, or the same animal under different conditions, has a period that is shorter than 24 hours, in which case the bars would look something like this. Day 1, day 2, day 3, day 4, day 5, and so on. In this case, of course, if you now do the same exercise of labeling the onsets of activity, the line that these onsets describe is drifting to the left, or in other words, the period for the animal to go from one onset of activity to the next onset of activity on day 1 to day 2 is less than 24 hours. Let's say in this case, we'll say that this was 23 hours and 0.7, okay, which is roughly 23 hours and 40 minutes. So what you can see from these two types of displays is that if the line drifts to the left, that means that the animal has a period that is less than 24 hours, right? Whereas if the line drifts to the right, this is a period that is longer than 24 hours, and therefore it's a long period. Typically we call this longer than 24 or shorter than 24. And you may say, well, that's weird. Why would an animal get on a wheel a little bit later every single day. It's almost like as if you were to go to bed an hour later every day and then wake up an hour later every day, which, by the way, there are some people that have that problem. We'll talk about that later. Um, well, it turns out that if you leave animals, including humans, without any cue about the light dark cycle or any other cycle outside of the room where they are, in other words, they have no external clues of time, they will express their endogenous clock period. In other words, none of, as we said in lecture, none of the periods are exactly 24 hours. Our clocks don't have the ability to tick at exactly 24 hours. So depending on the species and depending sometimes on the individual, the periods can either be longer or shorter than 24 hours. In humans, they are typically longer than 24 hours. So most humans, without any reference of time, will show an actogram like this, but for instance, mice have periods that are shorter than 24 hours and they will look like this. So that's essentially what we use actograms to. We use them to display raw data that can be activity, temperature, any kind of thing that you can measure for many, many days with a high frequency, like every few minutes. Sometimes there are some ways in which we use the actograms to display very peculiar activity in different ways. And I'll show you a couple of examples that you will see in many of the papers and many of the lectures that we'll be talking about throughout the lecture. So if we erase now, sometimes you will have animals or plants or whatever you're studying that have a period that is so different from 24 hours, let's say from 0 to 24, that the 24-hour actogram becomes too narrow. And basically, as we saw in the animals that had the longer period, let's say that you have an animal that has a period of a very long period, 28 hours. So each day the animal gets on the wheel about 4 hours later. Let's say that that's exactly 4 hours. I don't know whether that's the case. It's not to scale. So what's going to happen is that if you try to plot this, it will look like something like this, and it kind of becomes annoying because it's hard to visualize the whole bout of activity in one 24-hour plot. So sometimes what you do is what we call a double plot, or a double plotted actogram, where instead of having 0 to 24, you have 0 to 48. So there's now 48 hours. Okay, so day 1, day 2. And what you do is you plot on, this is day 1, you plot the activity of day 1, and then this would be day 2, you plot the activity of day 2, which would be a little bit later. So this bout that I'm drawing here is the same bout that I'm redrawing here, okay? And then the same will be true with day 3 here, and 4, and so on. So essentially what you will see is that now you will have the repeated dates. So this is day 1, day 2, day 2 again, day 3 again, day 4 again, day 5, and so on. But the advantage of this is that when you have a double plotted actogram, I'm going to redraw this, you could have just this bout of activity, the central bout here, and this will look like this. And the advantage of this is that now you can visualize very nicely the whole bout of activity, how it progresses. And you can, for instance, measure the slope of this curve to determine the period, or do other things that we'll see how we'll use it to estimate parameters of this rhythm. So this is what we call a double plotted actogram. You could even have a triple plotted, or as many successive days as you want, one next to the other. Other times people use other tricks to plot animals that have a period that is very different from 24 hours. So let's say now that we have an animal that has a period that is shorter than 24 hours, but much shorter. Let's say, you have a mutant, and there are some mutants like this, that has a period, a free running period or a circadian period that has something like 20 hours or even less. So basically, what you will see is that from day to day, these bars, again, they will go away from your 24-hour block very soon, because this period is very different, much shorter than 24 hours, right? One trick that you can use is to, once you have several days of activity, right, and you figured out that the period is shorter, you can measure this period. And let's say that you measured it with whatever method you use, and we'll talk about methods to measure period. And this period is exactly 19 hours. Okay, so that means that from onset of activity, as we said before, onset of activity to onset of activity, it takes this animal 19 hours to repeat, to start running on the wheel again. So one trick that you can use now is to replot the very same data. Okay, remember, you have this data in a computer, so you can plot it any way you want. But now, instead of using an actogram that has 0 to 24, you will use an actogram that has 0 to 19. Let's say that this would be here, 0 to 19. As slightly imagine that this gap here is 5 hours. Well, if you now replot the same data from 0 to 19, the first bout of activity will be here, and you know that the next bout started 19 hours later. So basically, in this case, these are not days, or if you want, they are 19-hour days. And what you see is that now, when you replot the very same data, now these become a vertical line, because what you did is artificially align the x-axis here with the period of the animal. So many times you will see actograms, you have to be very careful, actograms that have different x-axis length. In other words, you can do an actogram of 24 hours, which is the most typical thing you will always see, but you can also do actograms that have, say, an x-axis of 19 hours or 15 hours or 28 hours, depending on what period the animal has. So that's what we will essentially finish with for this crash course on actograms. Remember, this is going to be throughout the class. We'll be dealing with actograms, and it's very important that you understand how to read them very quickly, that as soon as you see an actogram, you know where the animal has a period that it's exactly 24 hours, different from 24 hours, and that you always know that vertically you have days or cycles, and that the x-axis is always time, but that time is not necessarily always 24 hours. Thank you, and I'll see you in class.